Hello, welcome to the second day of multiplying binomials, or in this case polynomials, because there may be some others. But before we do that, I want you to do a little warm-up math, just to remind you of some of the math that we've done this school year, especially this exponent stuff, combining like terms, distributive property, and a little bit more exponent stuff. Some of the stuff that you guys have really been struggling with. So go ahead and pause your video, do these 5 problems right now. Okay, so hopefully you took the time to do the problems. I can't guarantee you did, but if I were going to do this problem right here, I'm multiplying multiplying these polynomials. Here's a monomial times a monomial. So when I take 6 times 7, I know that's going to be 42, which means that A and B are wrong. And then I've got to multiply the A's, the B's, and the C's. This is B to the first, C to the first, A to the first, C to the first. So this will be 42, A to the 4 plus 1, B to the 1 plus 3, C to the 1 plus 1, or 42, A to the 5th, B to the 4th, C to the 2nd, which would be D. Problem number 2. Before we can combine our like terms, we need to take the inverse of the second quantity and rewrite everything without parentheses. So here's 7x squared plus 3x minus 4. The inverse of minus 2x is plus 2x squared, plus 6x minus 5. When I combine my 7x squared with my positive 2x squared, that's 9x squared. Positive 3x with positive 6x is plus 9x, and minus 4, the negative, see it, and the minus 5, that's minus 9. Problem number 3, the distributive property. If I take 3 groups of 4x squared plus 2x plus 5, and you can model it with a rectangle here. If I take 3 times 4x squared plus 2x plus 5, 3 times 4x squared is 12x squared. 3 times 2x is 6x. 3 times 5 is 15. So this, or you could do it that way, is 12x squared plus 6x plus 15. Problem 4, the inverse, the exact opposite of all this, would equal negative 5x to the third, negative 2x squared, and negative 3. And lastly, dividing. If you take 56 divided by negative 8, that's going to give me negative 7, And then my x to the 4th and x to the 1st is x to the 4 minus 1, y to the 2 minus 3, and z, which is already in the numerator, is just the first power. So this is negative 7, x to the 3rd, y to the negative 1st, z. But you can't end the problem with a negative 1 exponent. So we're going to take and use our rule, n to the negative 1 is 1 over n to the 1st, and get negative 7, x to the 3rd, z over y to the 1st. This is the best answer. Hopefully you got all those right, and let's move on. So yesterday, you can pause, take a look at your homework answers, see if you got all those right on your homework that you turned in. And now let's move on to this. So yesterday, we were learning how to multiply polynomials. In this case, binomials times binomials. There's two terms multiplied together. And we were going to use the composite rectangle. Composite rectangle requires us to put all of the detail into the picture. Well, that's great if it's x plus 2 times x plus 3, not too difficult. But what if I gave you x plus 15 times x plus 19? Well, drawing in all that detail to make this composite rectangle like we did yesterday would result in this picture right here, which would be horrible to have to draw. That means the composite rectangle is not a very good tool for drawing this. I mean, we know that the x by x dimension had to be the x squared. The x squareds were going up in this corner. And the x, the long side by 1, and the long side by 1, and the long side by 1, these were all x tiles, filling in 15 of them. And then going down this side, we had an x dimension by a unit, x by 1. That's why this piece is turned sideways along that long edge for 19 of them. And then over in here, we would have 19 by 15 unit tiles. But drawing it would not be a good use of your time. The whole goal of these area models is to make something that's usable every time very quickly. And this is not quick. Yesterday you saw that, it was tedious. So instead of using a composite rectangle, maybe we can find a shortcut way, maybe more like this. This is called a generic rectangle. Does it have all of the same details in it? So instead of using a composite rectangle, if we used a generic rectangle, something that allowed us to multiply or get the areas of the sections that we needed. So instead of 15x tiles being drawn here, I'll just write 15x. Instead of drawing 19x tiles, I'll write 19x. Instead of drawing 285 unit tiles, oh my gosh, that'd be horrible. I'm just going to write 285. Yay! So I end up then with the answer to this problem being x squared plus the total of my x's, well, that looks like 34 x's, plus 285. And I have a much easier drawing that I can draw quickly, because I'm going to need to do that to make sure that I get all of the multiplications. When I take a binomial times a binomial, I'm going to get 4 multiplications. Now those 4 multiplications result in 4 sections that get added together to result in a trinomial in this case. But there are ways to get 4-term polynomials. There's ways to make a binomial times a binomial end up in a binomial. But either way you do it, you need to make sure that the binomial times binomial has 4 multiplications. Your parents learned this as something called FOIL. This was called the first. This is the outer, the inner, and the last. So if you ask your parents about FOIL, first, outer, inner, last, this was what they learned, and we're going to learn it as a graphic organizer. So let's go and do a couple more examples and get you started on generic rectangles. So use generic rectangles. We want to be able to make this a tool that you could use every day frequently because it's super easy. So if I want to multiply x plus 1 times x plus 2, I know that this is like a length times a width. So we're talking about a rectangle, right? So as we're going to go do this, I'm going to start, instead of by drawing that little skeleton outline, I'm going to start by just drawing a rectangle. And on this side, I'm going to put x plus 1, and this one I'll put x plus 2. It doesn't matter which one you put them on. You could have it flipped and have the x plus 2 here and the x plus 1 over there. It doesn't really matter. You'll still get the same answer. So I know that with my pluses and minuses that's cutting it up into sections. So I'm going to cut a section at each of the pluses and minuses at each of the operations. Let me erase this little mark that I got right here. And then I'm going to go find the answer to each part. So if I have a x by x dimension, right in here, this is going to be x squared. If I have an x dimension by 2 units, how many x tiles will I fill in here vertically? Well, it's going to be 2x tiles. It's basically just like finding the area by taking this x times this 2. And then if I have a 1 by an x tile, that's going to be 1x. And if I have a 1 by a 2, 1 by 2, that'll be 2. So my answer, the product x plus 1 times x plus 2 will equal x squared plus 3x plus 2. That's your final answer as a product and as a sum. What I want to see on your paper when you do these problems is I want to see this work right here. Now, I mentioned yesterday there was something in science called Punnett squares, that genetic thing. So when you're looking at genetics, if I said that you had, A, B, and B, I don't know. I don't know what this is, but I just know that I learned this kind of the term. I'm not a science person, but I am a math person. So this genetic would be AA, this would be AB, this would be AB, and this would be BB. Basically, that's the exact same thing we were doing here, except I was doing XX, that's x squared. I was doing 2x, the 2 and the x, the 1 and the x, and the 1 and the 2. 1, 2. That's how I'm getting the 2. So as you multiply those together, you get each of these terms. Let's do a little bit more difficult problem. Hold on, I gotta back that up because I just deleted everything. There we go. So on the second example problem, start with a rectangle. I'll put my x plus 5 here and my 2x plus 7. And the way I'm going to cut this up is again at the pluses. Now, if you want to have this plus up here, you can. I usually don't, but in between the two terms, I'm going to cut this. And then I need to find the area of this box. So if I have a box that has a dimension that's x by 2x, you got to be thinking to yourself, what is x times 2x? X to the first times 2x to the first would be 2x squared. This dimension, x and 7, x by 7 would be 7x. And this 2x and this 5, the 2x and the 5, they make 10x. And the 7 and the 5 and the 7, they make 35. So my result of the x plus 5 times 2x plus 7 would equal 2x squared plus, combine your x's, 17x plus 35. This is the work. You can do this very quickly. Once you get enough practice at it, the generic rectangles really fly. And then the one last example I'm going to go ahead and give you here. If I asked you to multiply a monomial like x times 3x plus 7. Okay, there we go. Well, when you go to cut this up, here's x, here's 3x plus 7. This has one term, this has two terms. When you cut it at the terms, you're only going to get two boxes that you need to find the area of. Therefore, x, 1x times 3x will be 3x squared. 1x times 7 will be 7x. So the answer to this problem is 3x squared plus 7x. Now that you've seen enough examples here, you're going to go ahead and we'll have you do this generic rectangle. You're going to be doing problem WR71, and then you're going to do parts A, B, C, D, E, and F. When you finish, you can go ahead and work for a while also on the homework problems that you have, which are, I want you to read 72 on the resource page, read through this whole thing, make sure you understand it, and then do WR73 and WR81. I think 81 is a mix and match problem also. For each of these problems, show your generic rectangles. Ooh, generic rectangles. On every problem, I want to see the generic rectangles. Okay? So that's it for right now. Thank you for listening, and that's all we're going to do. Have a good day.